Welcome to Blueprint to Reality. In today's episode, we're tackling a critical topic for cities prone to earthquakes: seismic retrofitting. As the risk of earthquakes continues to challenge engineers, retrofitting is the solution for making older buildings and structures more resilient to seismic activity. But how exactly do engineers strengthen existing structures, and why is it so important? Let's break it down. Why is seismic retrofitting needed? First, let's talk about why seismic retrofitting is crucial. Many buildings were constructed before modern seismic design codes were in place. These structures, whether they're schools, hospitals, or bridges, are vulnerable to collapse during an earthquake. Without retrofitting, these buildings pose a huge risk to human life and infrastructure. Seismic retrofitting helps bring older structures up to today's standards, ensuring they can better withstand the powerful forces generated by earthquakes. Identifying weak points. The first step in retrofitting is to identify weak points. Engineers conduct detailed assessments, looking for structural vulnerabilities like soft stories, inadequate connections, or materials that don't respond well to seismic forces. For example, older concrete buildings often have weak connections between floors and walls, making them susceptible to shear forces. By identifying these vulnerabilities, engineers can develop targeted strategies to reinforce the structure. Common retrofitting techniques. Once weak points are identified, engineers employ a variety of retrofitting techniques to strengthen the building. Let's look at a few common methods. Base isolation. This involves placing flexible bearings or pads between a building and its foundation, allowing it to move independently of ground motion. It's like giving the building shock absorbers to cushion the impact of an earthquake. Shear walls. These are walls added to resist lateral forces. By increasing a building's lateral stiffness, shear walls help reduce the swaying motion that can cause collapse. Bracing systems. Engineers may also install steel or reinforced concrete braces to add rigidity to a structure, preventing excessive movement during seismic activity. Column and beam jacketing. Wrapping or jacketing columns and beams with materials like steel or carbon fiber strengthens them, increasing their load-bearing capacity and preventing failure under seismic forces. Impact of retrofitting. Seismic retrofitting isn't just about strengthening a structure, it's about saving lives and protecting essential infrastructure. Take the example of schools, hospitals, and emergency services buildings. Retrofitting these structures ensures they remain operational after an earthquake, providing critical services when they're needed most. Retrofitting also reduces repair costs in the aftermath of a quake, making it a long-term investment in safety and sustainability. Seismic retrofitting is one of the most effective ways engineers can protect communities from the devastating impact of earthquakes. By reinforcing existing structures, we not only preserve our infrastructure, but also safeguard the lives of those inside. That's the power of engineering in action. Thanks for watching Blueprint to Reality. Be sure to like, subscribe, and hit the notification bell for more insights into the world of civil engineering and structural design. Stay safe, and we'll see you in the next video. Welcome back to Blueprint to Reality. Today, we're talking about something that sounds like a contradiction, but isn't: tensile structures. How can something be lightweight yet incredibly strong? Get ready to discover the engineering magic behind these seemingly delicate but super durable structures. From iconic sports arenas to futuristic airports, tensile structures are popping up everywhere, and we're about to reveal why they're changing the game in architecture and engineering. What are tensile structures? First off, what are tensile structures? Imagine a fabric stretched tightly between 2 points. The material itself may not seem strong, but when tension is applied, it becomes incredibly rigid and can support huge loads. Tensile structures rely on tension, not compression, to stay stable. Unlike traditional buildings that use heavy materials like concrete or steel to support themselves, tensile structures use flexible materials like membranes or cables to create lightweight but super strong designs. The power of tension. Okay, so how does this work? Think of a suspension bridge. Those cables are under constant tension, and it's that tension that holds up the massive weight of the bridge. Tensile structures work in the same way, but instead of just cables, we use high-tech materials like EEFE, PTFE-coated fiberglass, or PVC-coated polyester. These materials are flexible when loose, but can become rock solid when pulled tight. Efficiency in design. Here's the genius part. Tensile structures are incredibly efficient. They use less material, meaning they're lighter and cheaper, but because they distribute forces evenly through tension, they can cover massive areas without needing heavy support columns. That's why you see them in places like stadium roofs, exhibition centers, and pavilions. Ever been to the Denver International Airport? That iconic white canopy is made from tensile membranes, and it's strong enough to withstand heavy snow and wind, all while looking sleek and modern. Advantages over traditional structures. So, why go tensile over traditional methods? For one, flexibility. Tensile structures can be stretched into complex, flowing shapes that would be impossible or insanely expensive to achieve with steel or concrete. Also, they're lightweight. This means you can cover large spaces without adding massive loads to the foundation. And get this, they're more eco-friendly. Less material, faster construction, and a lower carbon footprint. Real-world examples. Now, let's talk about some jaw-dropping examples. Check out the Millennium Dome in London. It's 320 meters in diameter, and its entire roof is supported by nothing more than steel cables under tension. Or the Allianz Arena in Munich. Its outer membrane is made of EDFE, and it's strong enough to handle extreme weather while being so light, it barely adds any weight to the structure. And it looks futuristic as heck, too. The future of tensile structures. As materials technology keeps improving, tensile structures will only get more impressive. We're talking about lighter, stronger, and more flexible designs that can be used for everything from disaster relief shelters to space exploration bases. So, next time you see a massive canopy or a sleek, curved roof, just remember, it might look light, but thanks to the magic of tension, it's tough as steel. That's it for today's episode of Blueprint to Reality. If tensile structures blew your mind, smash that like button, hit subscribe, and drop a comment on your favorite engineering feat. Thanks for watching, and we'll see you next time. Welcome to Blueprint to Reality. Today, we're diving into one of the most fundamental principles of structural engineering, load distribution in buildings. Every structure, whether it's a small house or a towering skyscraper, is designed to bear and distribute loads efficiently. Understanding how this happens is key to creating stable, safe, and long-lasting buildings. Let's break down the art of load distribution into simple concepts. What is load distribution? At its core, load distribution refers to how the weight, or load, in a building is spread across various structural elements. These loads come from everything: the materials used in the building itself, the furniture inside, and even external forces like wind or earthquakes. A well-designed structure ensures that these loads are evenly distributed so no part of the building is overloaded, which could lead to damage or even collapse. Types of loads. There are several types of loads that a building must handle. 1. Dead loads. These are permanent loads, like the weight of the building materials, concrete, steel, walls, floors, anything that remains in place throughout the life of the building. 2. Live loads. These are temporary or movable loads, such as people, furniture, or even snow on the roof. 3. Environmental loads. These include forces like wind, seismic activity, earthquakes, and even temperature changes that can cause expansion and contraction. Each type of load must be considered during the design process to ensure a building's stability. How load distribution works. Now, how does a building actually distribute these loads? It all begins at the roof and upper floors, where loads are first applied. From there, the loads are transferred to beams and columns, which act like the skeleton of the structure, carrying the weight downward. Next, the loads are transferred to the foundation, which spreads the load evenly into the ground. Think of it like a funnel. Loads move from a wide area at the top to smaller, concentrated points and then spread out again into the ground, preventing the building from sinking or shifting. Designers often use techniques like cantilevering, where part of a structure extends without support, to balance the load and prevent excess weight from accumulating in one spot. Importance of balanced load distribution. Why is all of this important? Simply put, balanced load distribution prevents structural failures. If a building's load isn't properly managed, you could have buckling columns, cracked walls, or uneven settling, all of which can lead to catastrophic results. So, next time you look at a tall skyscraper or even your own home, remember that there's an intricate system at work underneath it all, carefully designed to distribute and balance loads to keep the structure standing tall and strong. Thanks for tuning in to Blueprint to Reality. If you found this breakdown helpful, be sure to subscribe for more insights into the world of structural engineering.
See you next time.
Welcome to this short yet essential discussion about the impact of torsion on building stability. You've likely heard of forces like bending and compression, but today we're focusing on torsion, a twisting force that can cause significant problems if not properly managed in structural design. In the next few minutes, we'll explore what torsion is, how it affects buildings, and why engineers must consider it to ensure structural stability. What is torsion? Torsion occurs when a structural element, such as a beam or column, experiences a twisting force around its axis. Imagine twisting a dish towel by holding both ends and rotating them in opposite directions. That twisting motion is torsion. In buildings, torsion can be caused by uneven distribution of loads, wind forces, or even seismic activity. When torsion affects a structure, it can lead to significant instability if not properly accounted for in the design. How torsion affects building stability. So, what happens when torsion affects a building? If a structure experiences twisting forces that it wasn't designed to handle, components like beams and columns can deform or even fail. Torsional forces are particularly dangerous in tall, slender buildings or irregularly shaped structures, where the center of mass may be offset from the center of stiffness. This mismatch can lead to uneven twisting during events like high winds or earthquakes, creating dangerous stress concentrations in parts of the building. Torsional irregularities and their dangers. Torsion is especially problematic in buildings with torsional irregularities, meaning the structure isn't symmetrical or balanced. For example, if a building has a large, open area on one side and heavy, rigid walls on the other, it may twist more under certain forces. This uneven twisting can amplify stresses in parts of the building, leading to cracks, fractures, or even collapse. Engineers must design structures to minimize torsional irregularities by carefully placing walls, supports, and load-bearing elements to resist twisting forces. Engineering solutions to control torsion. So, how do engineers prevent torsion from compromising building stability? One solution is to ensure symmetrical design, so forces are evenly distributed. Another is to use elements like shear walls, bracing, or torsional dampers to resist twisting forces. In earthquake-prone areas, special attention is given to torsional effects, as seismic forces can cause extreme twisting, putting buildings at risk. By designing with torsion in mind, engineers can make buildings that remain stable even under challenging conditions. In conclusion, torsion is a powerful force that can severely impact a building's stability if left unchecked. By understanding how torsional forces affect structures and using smart design strategies to control them, engineers can ensure that buildings are strong, safe, and capable of withstanding twisting forces caused by wind, seismic activity, or uneven loads. Thanks for joining me today, and remember, structural stability isn't just about strength, it's about resisting every force, including torsion. The mathematics behind bending moments. Welcome to this short yet insightful dive into the mathematics behind bending moments. You might have heard about bending moments in structural analysis, but today we'll break it down into simple terms. By the end, you'll understand the basic mathematical principles that govern how forces cause bending in beams. Let's jump right in. What is a bending moment? A bending moment occurs when a force is applied to a structural element, like a beam, causing it to bend. Think of a diving board. When a person stands on the edge, their weight creates a force that makes the board bend downward. Mathematically, a bending moment is calculated as the force multiplied by the distance from the point of force application to the point of interest. It's often expressed as m equals F times d, where m is the moment, F is the force, and d is the distance. The moment equation explained. Let's break that equation down. The moment is measured in Newton meters, meaning the force in newtons is multiplied by the distance in meters. The distance, also known as the lever arm, plays a critical role. If the force is applied further away from the support, the bending effect is greater. Picture this. If you push on the middle of a beam, it bends less than if you push at the end. That's the lever arm in action, controlling the intensity of the bending moment. Understanding the sign convention. Now, bending moments aren't just numbers, they have direction, too. Engineers use a sign convention to keep track. Positive moments cause what we call sagging, where the beam curves downward. Negative moments cause hogging, where the beam curves upward. This helps when analyzing different points along the length of a beam, as forces might create different effects at different locations. The importance of bending moment diagrams. To visualize how moments change along the beam, we use something called a bending moment diagram. It shows how the bending moment varies with the distance along the beam. Peaks in the diagram indicate areas of maximum stress, where failure is more likely to occur. Understanding the mathematics of bending moments helps engineers design beams that can withstand these stresses. In summary, bending moments tell us how forces cause beams to bend, and the simple equation of m equals F times d helps us calculate these effects. The lever arm, sign convention, and bending moment diagrams are key tools for engineers when designing safe and reliable structures. Thanks for joining me in this quick exploration into the mathematics behind bending moments. Welcome to Blueprint to Reality. In today's episode, we're diving into some of the most shocking building collapses ever caught on camera. While we often take the stability of structures for granted, engineering failures can lead to sudden and catastrophic collapses. These events are rare, but when they happen, the footage serves as a stark reminder of the importance of structural integrity and design. Let's take a look at 3 of the most unforgettable building collapses ever captured on film. Sampoong Department Store Collapse, South Korea, 1995. Our first collapse is the Sampoong Department Store in Seoul, South Korea. In June 1995, this 5-story luxury department store collapsed during business hours, killing over 500 people. The shocking part? The collapse occurred in just 20 seconds. The footage shows the entire top floor buckling before the structure crumbled inwards like a house of cards. What went wrong? Investigations revealed that illegal construction modifications were made to the original design, weakening the building's support columns. This tragedy serves as a reminder of the dangers of cutting corners in engineering and construction. Hard Rock Hotel Collapse, New Orleans, 2019. Next, we have the Hard Rock Hotel collapse in New Orleans, which was under construction when tragedy struck in October 2019. Footage captured by nearby witnesses shows part of the upper floors collapsing onto the floors below, eventually sending a massive cloud of dust into the street. In this case, design flaws and improper load distribution were the main culprits. The collapse claimed 3 lives and sparked a massive investigation into the project's management and construction practices. Seeing this happen in real time emphasizes how crucial oversight and safety protocols are, especially in large projects. Surfside Condo Collapse, Florida. The Champlain Towers South collapse in Surfside, Florida, is one of the most recent and devastating building failures caught on camera. On June 24, 2021, part of the 12-story condominium suddenly collapsed in the middle of the night while residents were sleeping. Security footage shows the building crumbling in 2 stages, with part of the structure collapsing and moments later, the remainder falling down like dominoes. The collapse led to the deaths of 98 people. Investigations pointed to years of structural degradation, particularly in the foundation and concrete slabs, which were exposed to saltwater corrosion. This incident has since sparked a nationwide reassessment of building safety standards and inspection practices. Key lessons from these collapses. What can we learn from these tragedies? While each collapse had different causes, whether it was poor design, construction flaws, or a lack of maintenance, there's a clear takeaway. Building safety is non-negotiable. Cutting corners on materials, ignoring maintenance, or overlooking design flaws can have devastating consequences. Engineers, architects, and builders play a critical role in ensuring the long-term stability of every structure. These building collapses serve as harsh lessons in the importance of engineering, design, and safety inspections. The footage might be shocking, but it also reinforces the need for continual innovation and responsibility in the construction industry. Thanks for watching Blueprint to Reality. Don't forget to like, subscribe, and hit the notification bell for more insights into the world of civil engineering and structural design. Stay safe, and see you next time. Welcome back to Blueprint to Reality. Today, we're exploring a fundamental structure you've probably seen countless times without realizing how crucial it is to construction: the truss. Trusses are everywhere, on the roofs of homes, in massive bridges, and even in stadiums. But why are they so widely used? What makes this simple framework so powerful? Let's break it down. What is a truss? First, let's define what a truss actually is. A truss is a framework made up of triangular units connected at joints called nodes. The key to its strength lies in the triangle shape, arguably the most stable shape in engineering. Unlike a rectangle, which can easily be deformed, a triangle maintains its shape under pressure, distributing loads efficiently across its structure. This ability to distribute forces evenly is why trusses are incredibly effective at carrying heavy loads. Trusses in roofs. When it comes to roofing, trusses are a popular choice for both residential and commercial buildings.
Why?
It's all about efficiency. Roof trusses allow builders to span large distances without the need for internal supports like columns or beams. This means you get more open space inside a building. The triangular configuration helps distribute the weight of the roof evenly across the walls, reducing the chance of structural failure. In short, trusses help create stronger, lighter, and more cost-effective roofs. Trusses in bridges. Now, let's talk about bridges. Trusses are commonly used in bridge designs, especially truss bridges, which can span vast distances while holding heavy loads like vehicles and trains. The secret? Trusses efficiently distribute the weight of the bridge deck across multiple points, making the bridge capable of handling enormous forces. A great example is the Forth Bridge in Scotland, one of the most famous truss bridges in the world. It's been standing strong for over 130 years, thanks to its truss design, which handles the dynamic loads of trains and natural forces like wind. Efficiency and material use. Another reason trusses are so widely used is their material efficiency. Because of the triangular design, trusses can carry large loads while using relatively little material compared to other structural systems. This makes trusses more cost-effective without sacrificing strength. Builders can use lighter materials, reduce overall costs, and still achieve high levels of safety and durability. In both roofs and bridges, trusses have proven their worth over centuries. They offer an ideal balance between strength, efficiency, and material savings, making them an indispensable part of engineering. Next time you look at a roof or across a bridge, take a moment to appreciate the power of trusses that makes it all possible. That's it for today's episode of Blueprint to Reality. Be sure to like, subscribe, and hit that notification bell for more fascinating insights into the world of civil engineering and design. See you next time. Welcome back to Blueprint to Reality, where we explore the fascinating world of civil engineering and architecture. Today, we're diving into a crucial but often overlooked aspect of building design: geometry. How do shapes and forms influence the strength and stability of structures? Introduction to structural geometry. Geometry is more than just aesthetics in engineering. It plays a vital role in determining a building's ability to bear loads and resist forces like wind, earthquakes, and gravity. The shape of a structure, whether it's a bridge, a skyscraper, or even a simple beam, directly affects its strength and stability. Triangles, the strongest shape. Let's start with the triangle. Known as the strongest and most stable geometric shape, triangles distribute force evenly along their sides. That's why you see triangular forms in trusses, bridges, and towers. The triangle's rigidity ensures that, when pressure is applied to any of its corners, the force is spread out across the entire structure, preventing deformation. Engineers use triangular frameworks in roof trusses and bridge designs, creating a network of triangles that efficiently manage both tension and compression forces. Arches and domes. Mastering compression. Next, we have the arch and dome, two geometric shapes that excel at handling compression. In an arch, forces are funneled downwards and outwards, allowing it to support heavy loads with minimal material. That's why ancient civilizations like the Romans used arches extensively in their bridges and aqueducts. Domes, which are essentially 3D arches, spread compression across their entire surface, making them incredibly strong and efficient at supporting large areas. Modern engineers still rely on these shapes for large spans, like stadiums and domed roofs. Hexagons and efficiency. Hexagons are another fascinating geometric shape used in engineering. Found in everything from honeycomb structures to carbon nanotubes, hexagons provide a balance of strength and material efficiency. Their ability to tessellate without leaving gaps makes them ideal for creating lightweight, strong structures. Geometry is at the heart of structural strength, influencing how buildings withstand the forces of nature. Whether it's the stability of triangles, the compression power of arches, or the efficiency of hexagons, understanding geometry allows engineers to design safer, stronger, and more efficient structures. Thanks for watching Blueprint to Reality. If you're fascinated by the science behind engineering, don't forget to subscribe for more in-depth insights. Welcome to this quick yet essential dive into the world of material elasticity and its critical role in structural safety. From skyscrapers to bridges, every structure relies on the elasticity of its materials to ensure it can withstand the forces of everyday use and extreme events. In the next few minutes, we'll break down what elasticity means, how it affects structures, and why it's so important for safety. What is material elasticity? Let's start with the basics. Material elasticity refers to a material's ability to return to its original shape after being stretched or compressed. Think of a rubber band. When you stretch it and then let go, it snaps back to its original form. That's elasticity in action. However, not all materials behave exactly like rubber. Steel, concrete, and even wood have their own limits of elasticity, and understanding those limits is vital for engineers when designing safe structures. Elastic limit and structural safety. Now, every material has an elastic limit, the point beyond which it cannot return to its original shape. This is where things get critical. When a structure experiences forces, such as wind, weight, or even an earthquake, the materials within it stretch and compress. If those forces exceed the material's elastic limit, permanent damage can occur, compromising structural safety. Engineers must calculate the forces a building will face to ensure materials will only experience stress within their elastic limits. Young's modulus, the measure of elasticity. So, how do we quantify elasticity? Engineers use a value called Young's modulus. This measures a material's stiffness, or how much it will stretch under a given force. A high Young's modulus means the material is stiff, like steel, and resists deformation. A low modulus, like rubber, means the material is more flexible. By calculating Young's modulus, engineers ensure that the materials chosen for a structure can handle expected forces without losing their shape, ensuring safety under stress. Why elasticity matters for everyday structures. Elasticity plays a vital role in everyday structures. Take a suspension bridge, for example. The cables must stretch slightly to accommodate the weight of traffic, but they also need to snap back to maintain the bridge's integrity. Even in buildings, materials like steel beams and concrete must flex to handle loads and forces without permanent deformation. Properly accounting for elasticity ensures that structures remain both functional and safe. In conclusion, elasticity is more than just a material property, it's a cornerstone of structural safety. From defining the elastic limit to calculating Young's modulus, engineers rely on the elasticity of materials to design structures that are both resilient and reliable. Next time you cross a bridge or enter a skyscraper, remember that material elasticity is silently at work, keeping you safe. Welcome back to Blueprint to Reality. Today, we're diving into the engineering marvel behind the massive roofs you see in stadiums. Ever wondered how they manage to cover such huge spans without collapsing under their own weight? Let's unlock the secrets behind long-span roofs in stadiums. Introduction to long-span roofs. First, what exactly are long-span roofs? Simply put, these are structures designed to cover large areas without the need for internal supports. They give stadiums that wide, open feel, perfect for large crowds and events like sports and concerts. But how do engineers achieve this? The answer lies in smart design, advanced materials, and clever use of geometry. Key design techniques. One of the most common techniques is the truss system. Think of a truss as a web of triangles made from steel or aluminum. Triangles are strong and stable, so this network can distribute loads efficiently across the roof. Next, we have cable-stayed structures. These systems use high-strength steel cables to support the roof, almost like suspension bridges. You'll see these in stadiums where the roof needs to be lightweight but strong. Another impressive method is the geodesic dome. Pioneered by architect Buckminster Fuller, this design uses a lattice shell structure to cover large spaces while using minimal material. It's strong, energy-efficient, and iconic. Materials and innovation. Now, the materials play a huge role in making these roofs possible. Modern stadium roofs often use a combination of steel, aluminum, and advanced polymers like ETFE. ETFE is super light, transparent, and incredibly strong, perfect for letting natural light into the stadium while keeping the structure lightweight. Innovations like pre-stressed concrete and composite materials are also used to handle both the dead loads, the roof's own weight, and live loads, crowds, wind, snow. Engineering challenges. But, of course, these roofs come with challenges. Engineers have to account for factors like wind loads, seismic activity, and temperature changes. One wrong calculation, and the entire structure could be at risk. That's why precision in structural analysis and design is key. Advanced software simulations are often used to test the roof's stability under extreme conditions before construction even begins. Notable examples. Want to see these principles in action? Look at London's Wembley Stadium with its 315-meter steel arch, or SoFi Stadium in California, which uses a lightweight ETFE roof that covers over 70,000 seats. Each of these stadiums reflects the perfect balance between form and function, where aesthetics meet cutting-edge engineering. So, the next time you're in a stadium staring up at the massive roof, you'll know there's more going on than meets the eye. From trusses to cables, these long-span roofs are a testament to modern engineering and design. Thanks for tuning in to Blueprint to Reality. If you enjoyed learning about the secrets behind stadium roofs, hit the like button and subscribe for more engineering insights. See you in the next video. Structural engineering has witnessed some groundbreaking innovations over the last decade, revolutionizing how we design and build everything from skyscrapers to bridges. Today, we'll explore the top 5 structural engineering innovations of the decade that are pushing the limits of what's possible and reshaping our built environment. Let's dive in. Innovation number 1. Self-healing concrete. Our first innovation is self-healing concrete. Traditional concrete can crack over time due to stress, weather, or environmental factors. However, researchers have developed a concrete mix that contains special bacteria or chemical agents. When a crack forms, these agents activate to heal the damage by producing calcium carbonate, effectively sealing the cracks. This advancement significantly extends the lifespan of concrete structures, reducing the need for repairs and maintenance. Innovation number 2. 3D printed buildings. Next, we have the rise of 3D printed buildings. Using large-scale 3D printers, engineers can construct homes, offices, and even infrastructure in a matter of days. This innovation minimizes material waste, speeds up construction timelines, and allows for more customizable and complex designs. The potential for rapid construction in disaster-prone areas or regions with housing shortages is truly transformative. Innovation number 3. Carbon fiber reinforced polymers. Third on the list is the use of carbon fiber reinforced polymers, CFRP. This lightweight yet incredibly strong material is now being used to reinforce concrete and steel structures. Its high tensile strength and resistance to corrosion make it ideal for strengthening aging infrastructure. Engineers are now able to retrofit bridges and buildings more efficiently, ensuring they stand up to future demands without adding excessive weight. Innovation number 4. Modular construction. Fourth is modular construction. This method involves assembling prefabricated modules on-site, significantly reducing construction time and labor costs. The modules, built in controlled environments, are higher in quality and more sustainable. From apartment complexes to office towers, modular construction has proven to be an efficient and scalable solution for modern urban challenges. Innovation number 5. Smart structures. Finally, we have smart structures. These buildings and bridges are equipped with sensors that monitor stress, temperature, humidity, and vibrations in real time. This data allows engineers to make informed decisions regarding maintenance and safety. By detecting potential issues before they become critical, smart structures enhance the resilience of infrastructure, saving time, money, and potentially lives. These innovations are shaping the future of structural engineering, making buildings smarter, stronger, and more sustainable. From self-healing concrete to smart structures, the possibilities for engineering are endless. As technology continues to evolve, we can only imagine what new advancements await in the coming decade. Thanks for watching, and don't forget to subscribe for more insights into the fascinating world of engineering. Welcome to Blueprint to Reality, where we dive into fascinating engineering questions. Today, we're exploring what happens when you build a perfectly symmetrical skyscraper and why symmetry isn't always as perfect as it seems. Introduction to symmetry. Symmetry is often seen as the ideal in design: balance, harmony, and beauty. A perfectly symmetrical skyscraper, one that is identical on all sides, might seem like an engineering masterpiece. But when it comes to building tall structures, symmetry brings unique challenges that aren't immediately obvious. Structural and wind load challenges. In theory, symmetry distributes loads evenly throughout the building, which can make the design seem more efficient. However, the real world is rarely as perfect as the design. For instance, wind doesn't hit a building evenly from all directions. In fact, symmetrical skyscrapers are more prone to experiencing vortex shedding, a phenomenon where wind causes oscillating forces on the building. This can create dangerous swaying or even structural fatigue over time. To counteract this, engineers often incorporate aerodynamic features like tapered shapes or wind dampers, which help reduce the impact of wind forces, even in a symmetrical design. Foundation and ground settlement. Another issue is the ground itself. Soil conditions aren't always consistent beneath a structure. Even with a symmetrical design, uneven settlement can occur over time, leading to structural imbalances or stress points in certain areas. Engineers often need to use advanced foundation techniques, such as deep piling or geotechnical monitoring, to ensure the building stays level and secure. Why symmetry isn't always practical. While a perfectly symmetrical skyscraper looks balanced, its actual use may not be. The distribution of elevators, mechanical rooms, or even office space can create internal weight imbalances. Modern skyscrapers often incorporate asymmetrical elements not just for aesthetic reasons, but also to handle practical needs like wind resistance, sunlight optimization, and internal load distribution. So, what happens when you build a perfectly symmetrical skyscraper? While it may look flawless, engineers have to navigate unique challenges, from wind forces to ground conditions, to ensure it stands tall and strong. In the end, a bit of asymmetry can make a building much more stable and efficient. Thanks for watching Blueprint to Reality. If you're intrigued by the intersection of design and engineering, be sure to like and subscribe for more exciting content. Welcome back to Blueprint to Reality. Today, we're exploring one of the most critical forces in structural engineering: shear force. Whether you're building a simple house or a towering bridge, understanding shear force is essential for ensuring the stability of any structure. But what exactly is it, and why is it so important? Let's break it down. What is shear force? In simple terms, shear force refers to the internal force that acts along a structure's surface, causing two adjacent parts of the material to slide past each other. Imagine holding a deck of cards and pushing the top half sideways. The cards move relative to each other. That's the same idea as shear force in a structure. When external loads like wind, weight, or even earthquakes push on a building, shear forces occur inside the materials. How does shear force occur? Shear force is a direct result of loads acting on a structure. For example, when a beam is subjected to loads from above, part of the beam tries to move vertically, while the other part resists this movement. This creates shear forces within the beam, which can lead to cracks or even structural failure if not properly accounted for. Shear force diagrams help engineers visualize how these forces act along the length of a beam or structure. The higher the force in a particular area, the greater the risk of structural damage if not designed carefully. Why does shear force matter? Shear force matters because it directly affects a structure's ability to resist failure. If shear forces become too great for the materials to handle, the structure may experience 1. Shear cracking. This happens when materials break along a plane where the shear force exceeds the strength of the material. 2. Buckling. Shear forces can also cause structural elements like beams and columns to buckle or bend, leading to potential collapse. 3. Structural instability. Even small shear forces, if left unchecked, can weaken a structure over time, making it unsafe for continued use. To combat these risks, engineers use reinforcements like steel bars in concrete or diagonal bracing in tall buildings, designed specifically to resist shear forces. Shear force in everyday structures. You encounter shear forces every day, often without realizing it. Take a simple bridge, for example. As vehicles move across, the bridge experiences shear forces along its supports. In skyscrapers, wind creates lateral forces that introduce shear into the beams and columns. Engineers carefully calculate and design around these forces to ensure the structure can safely resist them. So, why does shear force matter? Because it's a silent but powerful force that can dictate whether a structure remains stable or fails catastrophically. Thanks for joining us today on Blueprint to Reality. Be sure to subscribe for more insights into the fascinating world of structural engineering.
See you next time.
Welcome to Blueprint to Reality. Today, we're diving into a topic that's both fascinating and crucial for civil engineers: why bridges fail. From ancient times to the modern era, bridges have connected people, economies, and cultures. But when a bridge collapses, it's a powerful reminder that even the best designs can fail under certain conditions. So, what causes these failures and what can we learn from them? Let's explore. Design flaws. One of the most common reasons for bridge failure is design flaws. Engineering is all about precision, and a small miscalculation in the design phase can lead to catastrophic results. Take the infamous Tacoma Narrows Bridge, which collapsed in 1940. Designers underestimated the effects of wind-induced vibrations, causing the bridge to twist uncontrollably and eventually fail. Modern design codes now account for aerodynamic forces, thanks to this lesson. Material failure. Materials can also be the culprit. Bridges are subjected to constant stress from vehicles, environmental conditions, and natural wear over time. In the case of the Silver Bridge collapse in 1967, a single steel I-bar cracked due to corrosion and material fatigue. This small failure triggered the collapse of the entire structure. It highlighted the importance of regular inspections and the need for materials that can withstand long-term stress. Poor maintenance. Even a perfectly designed bridge can fail if it's not maintained properly. The Morandi Bridge in Italy collapsed in 2018, killing 43 people. While the design was innovative for its time, the collapse was linked to poor maintenance and corrosion of key structural elements. Regular maintenance and inspections are essential to ensure the safety of bridges, but budget cuts and neglect can lead to deadly consequences. Environmental forces. Bridges must also endure environmental forces such as floods, earthquakes, and extreme weather. The Minnesota I-35W bridge collapse in 2007, which killed 13 people, was partly due to an inadequate design to handle the loads it eventually carried. Additionally, climate change poses new challenges as rising temperatures, more frequent storms, and increased flooding are putting extra pressure on aging infrastructure. Bridge failures are often a combination of multiple factors, whether it's design flaws, material issues, lack of maintenance, or environmental forces. But from these tragedies, we learn valuable lessons that help engineers design safer, more resilient structures. If we continue to push the boundaries of innovation while learning from past mistakes, we can build a future where bridges not only connect places, but protect the lives of the people who cross them. Thanks for tuning in to Blueprint to Reality. Don't forget to like, subscribe, and hit the notification bell for more insights into civil engineering and structural design. See you next time. Welcome to Behind the Scenes of Iconic Buildings, where we explore the hidden engineering brilliance that transforms architectural dreams into reality. Today, we'll dive into the structures of some of the world's most iconic buildings, revealing how they stand tall against gravity, weather, and time. 1. The Burj Khalifa. Let's begin with the Burj Khalifa in Dubai, the tallest building in the world. At 828 meters, it's an engineering marvel. But what makes it stand? Its Y-shaped design isn't just for aesthetics, it provides stability. The building uses a buttressed core structure. Essentially, 3 wings extend outward from a central core, each reinforcing the other, resisting the high wind forces at such extreme heights. Additionally, the building's tapering shape reduces wind load as it climbs higher, ensuring it sways safely rather than dangerously. 2. The Sydney Opera House. Now, let's head down under to the Sydney Opera House. Its stunning sail-like shells are a feat of structural engineering. These aren't simply curved panels. They're a series of precast concrete ribs. The engineers created a solution where each shell is a segment of a sphere. By using spherical geometry, the design simplified both construction and load distribution. It's the perfect marriage of form and function, blending art with practical engineering. 3. The Eiffel Tower. We can't talk about iconic structures without mentioning the Eiffel Tower. When it was built in 1889, many doubted the safety of such a massive iron structure. But Eiffel's team used a deep understanding of structural dynamics. The iron lattice reduces wind resistance while maintaining strength. Its unique design allows for slight movement during strong winds, distributing stress across the tower. That flexibility has kept it standing for over a century, proving that even metal structures can bend without breaking. These masterpieces of engineering are more than just beautiful, they're feats of innovation. From wind-resistant skyscrapers to geometrically inspired shells, these buildings embody the perfect balance between art and science. And next time you gaze upon one of these structures, you'll know just a little more about the brilliance holding them up. Thank you for joining us on this behind-the-scenes journey. Subscribe for more insights into the world of engineering and architecture. Exploring smart materials in civil engineering. Welcome to Blueprint to Reality, where we dive deep into the innovations shaping the future of civil engineering. Today, we're exploring a fascinating topic that's transforming the way we design and build structures: smart materials. These cutting-edge materials can adapt, react, and even heal themselves, pushing the boundaries of what's possible in construction. What are smart materials? Smart materials are engineered to respond to environmental stimuli such as temperature, stress, moisture, and light. Unlike traditional materials, these can adjust their properties in real time. Imagine concrete that can repair its own cracks or steel that strengthens in response to stress. These aren't just futuristic ideas, they're already being tested in real-world applications. One key example is shape memory alloys, which can return to their original form after being deformed. Think of bridges or buildings that can snap back after an earthquake, reducing structural damage. Self-healing concrete. Let's talk about a revolutionary innovation: self-healing concrete. Cracks are inevitable in any concrete structure, but what if the concrete could repair itself? Researchers have developed concrete that contains bacteria or special chemical agents that activate when exposed to water. When cracks form and moisture seeps in, the bacteria or agents produce limestone, effectively sealing the cracks. This has massive implications for reducing maintenance costs and prolonging the lifespan of structures like bridges, tunnels, and roads. Energy harvesting materials. Another exciting development is energy harvesting materials. These smart materials convert environmental energy into electricity, powering sensors or devices embedded in buildings. For instance, piezoelectric materials generate electricity when mechanical stress is applied, meaning a roadway or bridge could generate power simply from the pressure of cars driving over it. This technology could lead to self-sustaining smart infrastructure, reducing our reliance on external energy sources while improving real-time monitoring of structural health. Why smart materials matter. So, Why do smart materials matter for civil engineering? In short, they offer solutions for some of the biggest challenges in construction, improving durability, enhancing safety, and reducing maintenance costs. As these technologies evolve, we'll see smarter, more resilient structures that adapt to their environment and even anticipate potential issues. That's it for today's exploration of smart materials in civil engineering. Thanks for watching Blueprint to Reality. Be sure to subscribe for more cutting-edge insights into the world of civil and structural engineering. See you in the next video. Welcome to today's episode, where we'll delve into the innovative world of biocomposite materials in construction. As the demand for sustainable building practices grows, biocomposites have emerged as a promising solution. But what exactly are biocomposites, and how are they revolutionizing the construction industry? What are biocomposites? Biocomposites are materials made from a combination of natural fibers and a biopolymer matrix. These natural fibers can come from sources like flax, jute, hemp, or even agricultural waste, while the matrix is often derived from renewable resources such as starch or polylactic acid. This blend results in materials that not only reduce reliance on traditional plastics, but also offer unique mechanical properties. Sustainability benefits. One of the main advantages of biocomposite materials is their sustainability. The production of biocomposites has a lower carbon footprint compared to conventional materials like steel and concrete. Additionally, many biocomposites are biodegradable, which means they can return to the earth without leaving harmful residues. This is particularly important as we face increasing environmental challenges and strive for circular economy principles. Mechanical properties. Now, you might wonder about the performance of these materials. Biocomposites can possess excellent strength-to-weight ratios, making them suitable for a variety of applications. For example, biocomposite panels have been used in building facades, providing both insulation and structural support. Research has shown that certain biocomposites can even outperform traditional materials in specific applications, offering durability alongside environmental benefits. Applications in construction. So, where are biocomposites being used in construction today? Architects and engineers are exploring their use in everything from structural components to interior finishes. Biocomposite beams and panels can be used in lightweight structures, while biocomposite insulation materials provide thermal efficiency. Additionally, furniture made from biocomposites is gaining popularity, combining aesthetics with sustainability. Challenges and future prospects. However, the journey toward widespread adoption isn't without challenges. Some biocomposites can be more sensitive to moisture and temperature fluctuations than traditional materials. This raises questions about their long-term durability in various climates. Nevertheless, ongoing research is focused on improving the performance and longevity of these materials, paving the way for their broader use. In conclusion, biocomposite materials present an exciting frontier in the construction industry. Their potential for sustainability, coupled with promising mechanical properties, makes them an attractive alternative to traditional building materials. As we continue to innovate and prioritize eco-friendly practices, biocomposites could play a vital role in shaping the future of construction. Thank you for joining us on this exploration of biocomposite materials. Stay tuned for more insights into sustainable building practices in our next episode. Imagine a world where buildings, bridges, and homes are created layer by layer, directly from a digital design. That's not some futuristic dream. It's happening right now, thanks to 3D printing. In today's video, we'll explore how 3D printing is revolutionizing the field of structural engineering and what this means for the future of construction. 1. What is 3D printing? 3D printing, also known as additive manufacturing, is a process that builds structures layer by layer from a digital model. Traditionally, construction relies on subtracting material, think cutting, drilling, or molding. But with 3D printing, we add only what's needed, reducing waste and increasing precision. This method can use a variety of materials, from concrete to polymers and even metal. 2. Speed and efficiency. One of the biggest advantages of 3D printing in structural engineering is its speed. Projects that used to take weeks or months to complete can now be done in days. For example, 3D printers can construct the walls of a small house in less than 24 hours. This not only speeds up construction times, but also reduces labor costs. Less manual labor means fewer chances for human error, which translates into stronger, more accurate structures. 3. Sustainability. In a world where sustainability is a growing concern, 3D printing offers an eco-friendly alternative. Since this process uses only the material needed, it minimizes waste. Some 3D printers even use recycled materials, further reducing the environmental impact. Additionally, 3D printed structures are often designed with efficiency in mind, leading to energy savings during their life cycle. 4. Complex designs made simple. Another game changer is the ability to create complex and intricate designs that would be nearly impossible or prohibitively expensive using traditional methods. Curved walls, intricate lattice structures, and optimized load-bearing designs can all be printed with ease. This flexibility allows engineers to push the boundaries of architecture and design while maintaining structural integrity. The future of 3D printing in engineering. While 3D printing in structural engineering is still evolving, its impact is undeniable. Faster construction, reduced waste, and the ability to create complex designs are transforming the way we build. As the technology matures, we can expect to see even more impressive structures, from affordable housing to futuristic skyscrapers. The future of construction is here, and it's being printed, one layer at a time. Thank you for watching, and be sure to subscribe for more insights into the evolving world of engineering. Designing for a millennium. Can we build structures that last 1,000 years? Most buildings today are designed to last 50 to 100 years. But what if we aimed for 1,000? What would it take to create a structure so durable, so resilient, that it stands the test of time for generations? In this video, we'll break down the key principles behind designing buildings that could last for a millennium. 1. The secrets of ancient structures. Looking back, lessons from the past. Some ancient structures like the Egyptian pyramids, Roman aqueducts, and medieval castles have stood for thousands of years. What did they get right? A big part of their longevity comes from materials and design simplicity. They used durable materials like stone and took advantage of natural forms, like arches and domes, which distribute weight evenly and resist decay over time. But it's not just about copying the past. We need to adapt these lessons for modern times. 2. Material science and durability. Choosing the right materials. To build for 1,000 years, you need to select materials that can withstand the elements. While stone and brick have lasted centuries, modern engineers also turn to materials like ultra-high-performance concrete, UHPC, which is far stronger and more resistant to cracking than regular concrete. Advances in material science, like self-healing concrete and carbon fiber reinforcements, are designed to endure extreme weather and resist corrosion, ensuring long-term structural integrity. 3. Climate considerations and adaptability. Designing for a changing world. Climate change is an essential factor in designing long-lasting buildings. Extreme weather, rising sea levels, and temperature shifts can compromise structures. To ensure a 1,000-year lifespan, buildings must adapt. This means using resilient designs that account for flooding, extreme winds, and even earthquakes. Elevating structures, using sloping surfaces for water drainage, and building in flexibility for future technologies are all part of this sustainable approach. 4. Simplicity and maintenance. Simplicity and maintenance, the key to longevity. A crucial aspect of longevity is simplicity. Complex systems often break down faster. By sticking to simple, proven designs, maintenance can be minimized. Regular upkeep is essential for any structure, but designing with accessibility in mind ensures that future generations can easily repair and maintain buildings, even if technology changes. Building for the next millennium. Designing buildings that last 1,000 years requires a perfect blend of ancient wisdom and cutting-edge technology. It's about selecting durable materials, anticipating future environmental challenges, and ensuring ease of maintenance. While it's ambitious, creating structures that stand for a millennium isn't impossible. It's the ultimate legacy in engineering, building something that lasts for centuries to come. Subscribe to Blueprint to Reality for more deep dives into innovative structural design. Welcome to this video on how to manage risks in construction projects. Construction is inherently risky due to its complex nature, and effectively managing these risks is crucial for project success. In the next 3 minutes, we'll explore key strategies to identify, assess, and mitigate risks in construction. 1. Understanding risk in construction. First, let's define what we mean by risk in construction. A risk is any uncertain event that can impact the project's objectives, whether it's budget, schedule, or quality. Common risks include site conditions, regulatory changes, labor shortages, and material delays. 2. Risk identification. The first step in risk management is identification. Engage your project team early in the process. Conduct brainstorming sessions, review past projects, and utilize checklists tailored to your specific type of construction. Remember, the earlier you identify potential risks, the better prepared you'll be to handle them. 3. Risk assessment. Once you have a list of potential risks, the next step is assessment. Evaluate each risk based on 2 criteria: the likelihood of occurrence and the potential impact on the project. Use a risk matrix to categorize risks into low, medium, and high levels. This will help you prioritize which risks require immediate attention and which can be monitored over time. 4. Risk mitigation strategies. Now that you've identified and assessed the risks, it's time to develop mitigation strategies. Here are a few effective approaches. 1. Avoidance. Change your project plan to eliminate the risk altogether. For example, if there's a high risk of flooding at a site, consider relocating the project. 2. Reduction. Implement measures to reduce the likelihood or impact of the risk. This could include using high-quality materials or investing in advanced construction technology to streamline processes. 3. Transfer. Shift the risk to another party. This can be done through insurance or subcontracting. For instance, outsourcing certain tasks to specialized contractors can help transfer specific risks associated with those activities. 4. Acceptance. In some cases, it may be best to accept the risk, particularly if the costs of mitigation outweigh the potential impact. However, ensure you have contingency plans in place to address any issues that may arise. 5. Monitoring and review. Risk management is not a one-time activity. It requires continuous monitoring and review throughout the project lifecycle. Schedule regular risk assessment meetings to revisit and update your risk register. Encourage open communication among team members to report any new risks as they arise. In conclusion, effective risk management in construction projects involves thorough identification, assessment, and mitigation strategies, followed by continuous monitoring. By taking proactive measures, you can navigate uncertainties and enhance your project's chances of success. Thank you for watching. If you found this information helpful, please like and subscribe for more insights on construction management. Until next time, stay safe and keep building. Welcome to Innovations in Seismic Design, preparing for the big one. Today, we'll explore how engineers and architects are revolutionizing the way we design structures to withstand the forces of nature, specifically earthquakes. 1. The importance of seismic design. Earthquakes can cause devastating damage, leading to loss of life and significant economic repercussions. As urban populations grow, the importance of seismic resilience becomes paramount. The primary goal of seismic design is to protect buildings, infrastructure, and most importantly, human lives during seismic events. Historically, many structures have failed to withstand earthquakes, prompting engineers to rethink their approach. Innovations in seismic design are not just enhancements, they're necessities in our ever-changing world. 2. Base isolation techniques. One of the most groundbreaking innovations in seismic design is base isolation. This technique involves placing a flexible bearing system between a building's foundation and its superstructure. Essentially, the building floats on these isolators, allowing it to move independently from ground motion during an earthquake. Base isolators absorb and dissipate seismic energy, significantly reducing the amount of force transferred to the structure. This innovation has been successfully implemented in various high-profile buildings, including the San Francisco City Hall and the Taipei 101. The results? Dramatic improvements in structural performance during seismic events. 3. Damping systems. Another innovation making waves in seismic design is the use of damping systems. These systems are designed to absorb and dissipate vibrational energy. There are several types of dampers, including 1. Viscous dampers. These work like shock absorbers in a car, using a fluid to resist motion. 2. Base damping. This technique uses devices at the base of a structure to absorb energy from seismic waves. 3. Friction dampers. They absorb energy by creating friction between two surfaces. Damping systems can be retrofitted to existing buildings or incorporated into new designs, offering flexibility and adaptability in seismic resilience. 4. Smart materials and technologies. The emergence of smart materials is also transforming seismic design. These materials can respond to environmental changes and adapt accordingly. For instance, shape memory alloys, SMAs, can revert to a predetermined shape after being deformed, helping structures recover after seismic activity. Moreover, advanced monitoring technologies like sensors integrated into structures allow for real-time data collection. Engineers can analyze how buildings perform during an earthquake, leading to better designs and improved safety standards. 5. The future of seismic design. As technology advances, the future of seismic design looks promising. Innovations like artificial intelligence and machine learning are enabling engineers to predict seismic behavior more accurately and optimize designs accordingly. The integration of these technologies will not only enhance safety, but also contribute to more sustainable construction practices. By using advanced materials and designs, we can reduce resource consumption and waste in the building process. In conclusion, innovations in seismic design are crucial in preparing for the big one. From base isolation and damping systems to smart materials and cutting-edge technology, these advancements are revolutionizing how we approach earthquake resilience. As we continue to innovate and adapt, we can build safer structures that protect our communities and save lives. Thank you for joining us in exploring the future of seismic design. Welcome to Blueprint to Reality. Today, we're taking on a challenge that cities across the globe are grappling with: aging infrastructure. Bridges, roads, water pipes, and power grids, many built decades ago, are reaching the end of their intended lifespans. How do engineers solve this problem without completely rebuilding everything? Let's explore some innovative solutions that are helping keep our infrastructure safe and functioning. The aging infrastructure problem. Over time, materials wear down. Concrete begins to crack, steel corrodes, and wooden beams weaken. Much of the infrastructure we rely on today was built in the mid-20th century, designed to last around 50 to 70 years. Now, many of these systems are aging out, leading to more frequent repairs, shutdowns, and even failures. And it's not just about roads or bridges. Everything from water mains to electrical grids is facing the same issue, putting public safety and everyday life at risk. So, how are engineers addressing this problem? Key strategies for revitalizing infrastructure. Engineers are deploying a range of innovative strategies to breathe new life into aging infrastructure. Advanced materials. Engineers are using new materials to replace or reinforce traditional ones. For example, self-healing concrete contains tiny capsules that release a healing agent when cracks form, automatically repairing the damage. Retrofit and strengthening techniques. Instead of rebuilding from the ground up, engineers can reinforce existing structures. One technique is carbon fiber wrapping, where lightweight, ultra-strong carbon fiber is wrapped around columns, beams, or bridges to strengthen them without adding too much weight. Smart infrastructure. Embedding sensors into structures like bridges and tunnels allows for real-time monitoring. These sensors continuously track stress, vibration, and wear, allowing engineers to catch issues before they escalate into costly failures or closures. Modular and prefabricated solutions. In some cases, engineers are turning to modular construction to replace aging infrastructure more quickly. Prefabricated parts are built off-site and then transported and assembled, cutting down repair time and minimizing disruption to public services. Examples of innovative infrastructure solutions. One striking example is the I-35W bridge in Minnesota. After its collapse in 2007, the rebuilt structure was equipped with smart sensors to constantly monitor the bridge's health, alerting engineers to potential issues before they become dangerous. Another brilliant example is Tokyo's underground floodwater management system. The city built massive underground tunnels and reservoirs to divert floodwater during heavy rains, preventing the drainage system from being overwhelmed. These examples show that even aging infrastructure can be upgraded and sustained with smart, innovative approaches that extend its lifespan. In conclusion, while aging infrastructure presents a complex challenge, engineers are finding innovative solutions to keep our cities running smoothly. From advanced materials to smart systems, these breakthroughs are helping ensure our infrastructure is safe, reliable, and efficient for years to come. Thanks for joining us on Blueprint to Reality. Don't forget to like and subscribe for more engineering insights. Welcome to Blueprint to Reality. Today, we're diving into one of the hottest topics in sustainable construction, cross-laminated timber, or CLT for short. This innovative material is rapidly gaining popularity for everything from homes to high-rises.
But why?
What makes CLT so special? Let's explore the remarkable benefits of using cross-laminated timber in modern structures and why it's poised to revolutionize the building industry. What is cross-laminated timber? First, let's get a quick overview. Cross-laminated timber is made by gluing together layers of solid wood boards at right angles. This crisscross pattern creates panels that are incredibly strong, durable, and lightweight. CLT panels are prefabricated, meaning they are made in a factory and then transported to the building site, ready to be assembled like giant wooden Lego blocks. So, what are the benefits of this material? Benefit number 1. Strength and stability. Don't let the word timber fool you. CLT is remarkably strong. Its multi-layered construction allows it to carry heavy loads while remaining flexible. Engineers often compare its strength to concrete and steel, but with one key advantage: it's much lighter. Because of this, buildings can go up faster, with fewer heavy cranes or equipment needed to transport materials. Plus, CLT's stability comes from its ability to resist warping, twisting, or swelling, making it an excellent choice for long-term durability. Benefit number 2. Sustainability. One of the biggest reasons for CLT's rise in popularity is its environmental impact. Timber is a renewable resource, and when sustainably harvested, it's much more eco-friendly than traditional materials like concrete or steel, which have higher carbon footprints. In fact, CLT panels actively store carbon, locking it away for decades, which helps reduce greenhouse gases in the atmosphere. The production process for CLT also uses less energy, making it a go-to choice for architects looking to build green. Benefit number 3. Speed of construction. Because CLT is prefabricated, the building process is much faster than traditional methods. Panels arrive at the site ready to be installed, reducing construction time significantly. This cuts down labor costs and allows buildings to go up in a fraction of the time. For example, a 10-story residential building made from CLT can be assembled in just a few weeks. That's not just fast, it's revolutionary for the construction industry. Benefit number 4. Fire resistance. You might think timber wouldn't perform well in a fire, but here's where CLT shines. In the event of a fire, the outer layer of CLT chars, which creates a protective barrier. This slows the fire's spread and keeps the inner layers intact for much longer than you'd expect. This self-protecting charring effect makes CLT surprisingly resilient to fire, giving occupants more time to evacuate and helping engineers design buildings that meet strict fire safety codes. Benefit number 5. Design flexibility. CLT offers tremendous flexibility in design. Its large panels allow for wide, open spaces without the need for too many interior columns. Architects and engineers love it because it enables the creation of innovative, modern designs that are also highly functional. Whether you're building a sleek office tower or a cozy residential home, CLT opens up new possibilities in how spaces can look and feel. In conclusion, cross-laminated timber is transforming the construction world. Its strength, sustainability, speed of construction, fire resistance, and design flexibility make it a game changer in both residential and commercial buildings. As we move toward a more sustainable future, CLT is leading the way as an eco-friendly, high-performance material. So, the next time you see a modern wood building, remember, there's more to it than meets the eye. Thanks for tuning in to Blueprint to Reality. Don't forget to like and subscribe for more engineering insights and innovations. Hello everyone and welcome back to our channel. Today, we're exploring a critical topic in civil engineering, the challenges of building in high seismic zones. With earthquakes posing significant risks to lives and infrastructure, understanding these challenges is vital for engineers, architects, and builders alike. 1. Understanding seismic zones. First, let's briefly define what high seismic zones are. These are areas where the risk of experiencing strong earthquakes is higher due to tectonic plate activity. Regions along fault lines, such as the San Andreas Fault in California or the Himalayan region, are prime examples. In these areas, buildings must be designed to withstand not only the forces of gravity, but also the unpredictable and intense forces generated by seismic events. 2. The importance of structural design. When designing structures in high seismic zones, engineers face several challenges. 1. Material selection. One of the primary challenges is selecting appropriate materials. Traditional building materials may not provide the flexibility and strength needed to absorb and dissipate seismic energy. Engineers often opt for materials like reinforced concrete and steel, which can withstand dynamic loads. However, the cost and availability of these materials can vary, complicating the design process. 2. Dynamic loads and forces. Next, engineers must consider the dynamic loads and forces that an earthquake exerts on a structure. Unlike static loads, which are constant, dynamic loads can change rapidly and unpredictably. This requires advanced analysis and modeling techniques to accurately predict how a building will respond during an earthquake. 3. Design codes and regulations. Another significant challenge is navigating design codes and regulations. Building codes in seismic zones are often stringent and continually evolving based on new research and technology. Engineers must stay updated on the latest codes, which can vary by region and may require detailed documentation to ensure compliance. This can add time and complexity to the design and construction process. 4. Innovative design solutions. To tackle these challenges, engineers and architects have developed innovative design solutions. 1. Base isolation. One effective method is base isolation, where a building is designed to move independently of ground motion. This involves placing flexible bearings or isolators between the building and its foundation, allowing it to absorb seismic forces. 2. Damping systems. Another approach is the use of damping systems, which dissipate energy during an earthquake. These systems can include tuned mass dampers, which are large weights installed within a building to counteract vibrations, and viscous dampers, which absorb energy through fluid motion. 3. Reinforced structures. Additionally, engineers often employ reinforced structures, using cross-bracing or shear walls to enhance stability and rigidity. These elements help distribute seismic forces throughout the structure, minimizing potential damage. 5. The human element. Beyond technical challenges, there's also the human element to consider. Public perception and understanding of seismic risks can influence building practices. In some cases, communities may resist certain design measures due to cost or aesthetics, putting additional pressure on engineers to balance safety with public preferences. In conclusion, building in high seismic zones presents numerous challenges, from material selection and design codes to innovative engineering solutions. By addressing these challenges head-on, we can create structures that not only withstand seismic forces, but also protect lives and communities. Thank you for joining us today. If you found this discussion insightful, please like, share, and subscribe for more content on engineering and construction topics. Together, let's build safer, more resilient structures for the future. Welcome to Blueprint to Reality. Today, we're diving into a revolutionary approach that's changing the way cities grow: modular construction. If you've ever wondered how we could tackle urban development challenges like housing shortages, rising construction costs, and sustainability concerns, modular construction might just be the answer. 1. What is modular construction? So, What exactly is modular construction? Simply put, it's a method where buildings are constructed in sections or modules, off-site in a factory setting. These modules are then transported to the final location and assembled like building blocks. Think of it like large-scale Lego for grown-ups, but with buildings. Each module is designed with precision, fully equipped with plumbing, wiring, and finishes before it's even shipped to the construction site. 2. Speed and efficiency. One of the biggest impacts of modular construction on urban development is its speed. Traditional construction can take months, even years. But with modular methods, up to 60 to 90% of the building process happens in a factory, while site work, like foundation preparation, happens simultaneously. This means buildings go up 50% faster than conventional methods, which is a game changer for rapidly growing cities. For urban areas facing housing crises, the ability to deliver quality homes in a fraction of the time is monumental. 3. Cost-effectiveness. Now, let's talk dollars and cents. Modular construction can significantly reduce costs due to the controlled factory environment. Unlike traditional construction sites, which are vulnerable to weather delays and labor shortages, modular construction is more predictable. Fewer delays, less waste, and better quality control lead to cost savings. And for cities struggling with budget constraints, this means more infrastructure can be built within the same financial resources. 4. Sustainability and environmental impact. Another major benefit is sustainability. Because modules are constructed off-site, material waste can be reduced by up to 50% compared to conventional methods. Additionally, the factory setting allows for better energy efficiency as materials are reused and recycling is more easily integrated. When applied on a larger scale, modular construction could help urban areas reduce their carbon footprint and promote greener development. 5. Flexibility and future growth. Lastly, modular buildings offer incredible flexibility. Modules can be easily added, removed, or reconfigured as the needs of a city evolve. This adaptability is key for fast-growing urban areas. Whether it's schools, hospitals, or apartment complexes, modular construction can quickly respond to changing demands. The ability to build up instead of build out means cities can maximize their use of space without overwhelming existing infrastructure. In conclusion, modular construction is reshaping the future of urban development. With its speed, cost-effectiveness, sustainability, and flexibility, it's poised to be a critical tool in addressing the challenges cities face today. Thanks for tuning in to Blueprint to Reality, where we turn concepts into solutions. Until next time. The importance of structural integrity in building design. When we walk into a building, whether it's a home, office, or towering skyscraper, we often take for granted that it will stand strong. But behind every safe structure is one key factor: structural integrity. What does that mean, and why is it so important in building design? In this video, we'll break down why ensuring a structure's integrity is essential to safety, longevity, and efficiency. Structural integrity. Structural integrity is a building's ability to withstand the loads and stresses it encounters without failing. It's not just about holding up the building's own weight, but also accounting for external forces, like wind, earthquakes, and even daily use by people and machines. If a structure lacks integrity, it's vulnerable to collapse or damage, posing serious risks to anyone inside or nearby. Why it matters. The consequences of poor structural integrity can be devastating. Think of well-known structural failures, like the collapse of bridges, stadiums, or even residential buildings. Often, these tragedies stem from poor design, material fatigue, or a lack of regular maintenance. When structural integrity is compromised, not only are lives at risk, but the economic cost of rebuilding or repairing can be astronomical. Key design considerations. So, how do engineers ensure structural integrity? It all starts with careful planning. Every element of a building, whether it's the foundation, beams, columns, or walls, must be designed to handle the forces it will experience. The materials chosen must have the right properties for strength and durability. Engineers also conduct stress tests and simulations to make sure the design can withstand extreme conditions, from heavy storms to seismic activity. Modern advancements in structural design. Today, advancements in technology are enhancing how we assess and ensure structural integrity. From finite element analysis, FEA, to building information modeling, BEM, engineers can predict potential weak points before construction even begins. With these tools, we're able to create safer, more reliable structures that stand the test of time. In the world of architecture and construction, structural integrity is the backbone of safety and reliability. Without it, even the most stunning designs could fail. Whether it's a small home or a massive skyscraper, prioritizing structural integrity ensures that we can live and work in environments that not only look good but also stand strong, no matter what comes their way. Welcome to the world of super tall buildings, the skyscrapers that define modern skylines and stretch engineering to its limits. 1. What makes a building super tall? A super tall building is defined as any structure over 300 meters or about 1,000 feet. But it's not just the height that makes them extraordinary. These buildings symbolize human ambition, pushing both architectural design and engineering to new extremes. From the iconic Burj Khalifa in Dubai to the Shanghai Tower in China, these skyscrapers aren't just feats of design, they're monumental achievements in engineering. 2. The engineering behind super tall structures. So, what exactly does it take to build a super tall building? It starts with the foundation, a massive concrete base that extends deep into the earth, anchoring the tower against wind and seismic forces. But as buildings soar higher, they face enormous challenges. Wind is a major factor. Engineers must design innovative solutions like aerodynamic shapes and tuned mass dampers, giant weights inside the building that sway opposite to the wind, keeping the structure stable. Another key aspect is the material used. From steel-reinforced concrete to advanced carbon fiber composites, engineers push the limits of materials to make these buildings not only taller but also lighter and more resilient. 3. Innovations driving the next generation of skyscrapers. As engineers continue to build higher, innovation becomes critical. New technologies like 3D printing and modular construction allow parts of these massive structures to be prefabricated, making the process faster and more efficient. Green building technologies are also playing a vital role. Super tall buildings are now being designed with sustainability in mind, integrating features like wind turbines, solar panels, and advanced insulation systems to reduce their environmental impact. 4. The future of super tall buildings. So, what does the future hold for super tall buildings? The next frontier lies in building even higher, perhaps even reaching a kilometer or more into the sky. As urban populations grow, the demand for vertical living spaces will only increase, driving engineers to explore new ways to push the limits. But it's not just about height. Engineers are also thinking about how these buildings will interact with their environments, how they can be smarter, more sustainable, and better integrated into the cities of tomorrow. Super tall buildings represent the pinnacle of modern engineering. They are more than just structures. They are symbols of human ingenuity and determination to reach new heights. As engineers continue to push the limits, one thing is clear: the sky is no longer the limit, but just the beginning. Welcome to today's discussion on an exciting and transformative topic in the construction industry: the role of robotics in modern construction. As we dive into this subject, we'll explore how robotics is reshaping building practices, improving efficiency, and enhancing safety on construction sites. 1. The evolution of robotics in construction. Robotics in construction isn't a new concept, but its application has evolved significantly over the years. Initially, robotics focused on simple tasks, such as material handling and basic assembly. Today, however, advanced robotics can perform complex tasks, from bricklaying to even autonomous vehicle operations. This shift has been made possible by advancements in AI, machine learning, and sensor technology, enabling robots to work more intelligently and adapt to various environments. 2. Benefits of robotics in construction. The benefits of integrating robotics into construction processes are numerous. First and foremost is efficiency. Robots can work tirelessly, completing tasks faster than human workers. For instance, robotic bricklayers can lay bricks with precision and speed, significantly reducing construction time for masonry projects. Next is safety. Construction sites are often hazardous environments. By deploying robots to handle dangerous tasks such as demolition or operating heavy machinery, human workers are kept out of harm's way. This not only reduces workplace injuries, but also minimizes the risks associated with strenuous labor. Moreover, robotics can lead to cost savings. While the initial investment in robotic systems may be high, the long-term savings achieved through reduced labor costs, minimized material waste, and enhanced project timelines can outweigh these costs. 3. Real-world applications. Let's look at some real-world applications of robotics in construction. One prominent example is automated drones. These drones are used for site surveys, inspections, and monitoring progress. They can quickly collect data and provide real-time insights, allowing project managers to make informed decisions. Another innovative use is in 3D printing. Robotic 3D printers can create entire structures or components by layering materials. This method not only reduces construction waste, but also allows for intricate designs that would be difficult or impossible to achieve through traditional methods. Additionally, companies like Construction Robotics have developed robotic arms that can assist workers in tasks like concrete pouring and surface finishing. These robots enhance precision and reduce fatigue for human workers, increasing overall productivity on the site. 4. Challenges and future prospects. Despite the many advantages, integrating robotics into construction does come with challenges. There are concerns about the high initial costs and the need for specialized training for workers to effectively collaborate with robotic systems. Furthermore, there is an ongoing debate about the impact on employment. While robotics may replace some jobs, they can also create new roles focused on managing and maintaining these advanced systems. Looking ahead, the future of robotics in construction is promising. As technology continues to advance, we can expect to see even more sophisticated robots capable of handling a wider variety of tasks. The integration of AI will likely lead to smarter robots that can learn from their environments and improve their performance over time. In conclusion, the role of robotics in modern construction is both transformative and essential. By improving efficiency, enhancing safety, and reducing costs, robotics is setting a new standard for how we build. As we embrace these advancements, the construction industry is poised for a future that not only enhances productivity, but also prioritizes the safety and well-being of its workforce. Thank you for joining me in this exploration of robotics in construction. Have you ever wondered why some projects finish on time and within budget, while others drag on for months and cost way more than expected? The secret lies in something simple but powerful: project scheduling. 1. What is project scheduling? At its core, project scheduling is the process of organizing tasks, resources, and timeframes to ensure that a project is completed efficiently. It's like a roadmap that guides you from start to finish, highlighting all the critical steps along the way. When you break down a project into manageable tasks, you can prioritize, assign deadlines, and keep the entire team aligned with the overall goals. Without a schedule, even the most well-planned project can quickly fall apart. 2. Why is project scheduling important? Now, why does scheduling matter so much? First off, it creates structure. Imagine building a skyscraper. You can't pour concrete before laying the foundation, and you definitely can't install windows before the walls go up. A well-defined schedule ensures tasks happen in the right order, avoiding chaos and rework. But that's not all. Scheduling helps to track progress, manage resources, and identify potential risks before they become major problems. When a task is delayed, you can adjust the timeline to minimize the impact on the rest of the project. This flexibility is key in keeping things on track. 3. Consequences of poor scheduling. On the flip side, poor scheduling, or no scheduling at all, can be disastrous. Without a clear plan, deadlines can be missed, budgets can skyrocket, and team morale can plummet. Think about it. When no one knows what to do next, confusion sets in. And confusion often leads to mistakes. Projects can run over budget, over time, and, worst of all, fail to meet the expectations of clients or stakeholders. It's like setting off on a road trip with no map or GPS. You might eventually reach your destination, but you'll waste time and resources along the way. How to create an effective schedule. So, how do you create a schedule that works? Start by identifying all the tasks that need to be completed, from the smallest to the largest. Next, assign deadlines to each task, keeping in mind dependencies. Some tasks must be finished before others can begin. Don't forget to allocate resources, whether that's manpower, equipment, or materials. Regularly review and update the schedule as the project progresses. This keeps everyone informed and allows for quick adjustments if something unexpected comes up. A flexible schedule is a successful schedule. The power of scheduling. In the end, project scheduling isn't just about timing, it's about coordination, communication, and control. With a solid schedule in place, you can steer your project toward success, delivering results on time, within budget, and with less stress. So next time you're faced with a big project, remember, the schedule is your best friend. When you gaze at a towering skyscraper piercing through the clouds, you might think its biggest battle is against gravity. But there's a silent force constantly at war with these giants: wind. This invisible enemy can make or break a tall structure. Welcome to Understanding Wind Loads, the silent enemy of tall structures. 1. What are wind loads? Wind loads refer to the pressure and forces exerted by wind as it flows around a building. The faster the wind, the more force it applies. But it's not just a steady breeze we're talking about. Wind is unpredictable. Gusts can slam into a building from different angles, creating areas of high pressure on one side and suction on the other. Tall structures, like skyscrapers, experience these forces more intensely. The higher you go, the stronger the wind, and this can create problems if not properly accounted for during the design process. 2. The danger of wind-induced vibrations. One of the biggest dangers of wind loads isn't just the direct pressure, but the vibrations they can cause. When wind hits a building at just the right speed, it can create something called vortex shedding. This phenomenon can cause a building to sway and shake, sometimes violently. Without proper design, wind-induced vibrations can lead to structural fatigue, cracks, and in worst cases, catastrophic failure. Imagine a massive tower moving back and forth like a reed in the wind. It's terrifying, but it's exactly what engineers work to prevent. 3. How engineers combat wind loads. But fear not, engineers have developed clever solutions to fight back against wind. One of the most common tools is the use of aerodynamic design. Rounded corners and tapered tops help reduce wind pressure and keep the structure stable. Another brilliant technique? Tuned mass dampers. These are giant weights placed at the top of a building that sway in the opposite direction of the wind-induced movements, counteracting the vibrations. It's like a balancing act at a massive scale. Some buildings even use perforated exteriors or gaps in the structure to let the wind pass through, minimizing pressure and turbulence. These design tricks turn wind from a fierce enemy into just another factor engineers can control. 4. Why wind load matters to you. So, why does this matter? As we continue to build taller, wind loads are becoming an even bigger challenge. And in a world dealing with climate change, stronger storms and unpredictable weather patterns mean wind loads could become more dangerous than ever before. Whether you're an engineer, a student, or just someone fascinated by skyscrapers, understanding wind loads gives you a glimpse into the invisible battles that happen every day above our heads. The next time you look at a skyscraper, remember, it's not just standing tall by chance. It's fighting the wind and winning. In the silent war between wind and structure, engineers are the unsung heroes, ensuring our buildings withstand the forces of nature. So, the next time you see a skyscraper, know that it's more than just steel and glass. It's a testament to human ingenuity.